I guess, you know, coronavirus combined with like boring tech topics and only 1 hour long. You know, you can always catch me after for more detail, because we don't have that much time to go into it. So today we're going to talk about CBC Casper liveness, or you know, liveness in CBC Casper. CBC Casper is a consensus protocol that I've been working on for the better part of like 3 to 4 years. Today is like the first time that I'm really sharing in public in detail the basic strategy and philosophy behind the CBC Casper liveness proposals or solutions, at least behind my favorite CBC Casper liveness solutions. There's been a number of these solutions that I'm not sharing today. I'm just sharing specifically like my favorite liveness solutions. Here's kind of roughly the outline of the talk. I do have a future work and conclusion section that's not mentioned here. Basically, I'm going to talk a little bit about liveness and consensus protocols and like what is this problem that we're trying to solve or that we've solved, and kind of how is it defined? How would you prove such a thing? And then I'm going to give CBC Casper liveness, kind of live CBC Casper specification in synchrony and in partial synchrony. And with any luck, we'll be able to get through all of it. And they're both very similar, and so probably I'll rush through the second one if we don't have that much time. So let's talk about liveness. What is liveness? Well, liveness basically refers to something eventually happening. In a consensus protocol, this something is a decision. So a consensus protocol is live if it eventually makes a decision. In the blockchain world, that means that it eventually finalizes a new block. In a binary consensus protocol, it means that it eventually decides on a bit. And decisions in these the consensus protocol context are kind of, at least I'm assuming, and are assumed here to be kind of final. And so the only real requirement for liveness is that in all protocol execution traces, there is a finite position in which there is a decision. So if you consider every possible protocol execution trace, every single way that the protocol could evolve, and for every single one, there's an index in that trace where there's a decision, then it's live. And specifically, I'm not talking about incomplete protocol execution traces, specifically complete ones. So a complete protocol execution trace has either two ways that it can look. Either as an infinite trace, or it terminates in a state with no transitions available from it. So complete protocol execution traces are like protocol execution traces that are either kind of infinite or terminating. So if you look at a protocol's complete traces, if every single one of them at a finite index has a decision, then it's live. That's like the definition of liveness. In our context here. Empty slide, just in case. Hopefully there wasn't anything on there. So basically, if there's a single trace without a decision, then the protocol is not live. So liveness is this really strong property. It talks about every single protocol execution trace. Even a single counter example will kind of throw a wrench in your gears. So there's this key theorem called FLP impossibility that shows that for deterministic or non-probabilistic, non-deterministic consensus protocols, it's impossible to have non-triviality, consistency, and liveness in an asynchronous network with a single faulty node. This is kind of like a super famous impossibility result in consensus, and people were basically, people thought like, oh, look, consensus is impossible. This is kind of like the way it was branded. Just to talk a little bit about these terms, non-triviality means that the consensus protocol can decide on mutually exclusive outcomes. So for a binary consensus protocol, that means like there is a trace where it decides 0, and there is a trace where it decides 1. Consistency means that in a single trace, the different nodes all make the same decision, or that they don't make inconsistent decisions in a single trace. So it's impossible, according to this theorem, to have all three: non-triviality, consistency, and liveness. In an asynchronous network, what that means is basically that any message that's sent is eventually received. So if you look at a complete trace, any message that's sent, has been received. But if you look at, say, a partial trace, and there's a message that's been sent but hasn't been received yet, in an asynchronous network, you're guaranteed that it'll eventually be received, although you may not know, in what amount of steps of the execution. So in a complete network, in an asynchronous network, in a complete trace, all the sent messages are received. And there's no additional kind of constraints on the order in which the messages are received. Or in the context of faulty nodes, if they are sent and received between correct nodes. So if they're sent and received between nodes that aren't synchronization faulty, then what that means is that in a complete execution trace, there will be a receive for every send. So CBC Casper is constructed to be safe in an asynchronous network with a limited number of faults. And because of the kind of non-probabilistic, non-deterministic nature of the protocol, this means that we can't also be live in asynchrony. This is what kind of FLP impossibility means. And then what we're going to do instead is we're going to follow a very similar design philosophy that we did for the original construction of CBC Casper for consistency, to construct validator strategies that are live in synchronous and partially synchronous networks, where we don't have this impossibility result applying. And we'll kind of get to see the kind of trick that we're able to do here that's impossible to do in an asynchronous network. That's liveness, that's the context. We can't really achieve liveness in asynchrony, so we're going to do it in partial synchrony and synchrony, which I'll describe in a moment. So, CBC Casper liveness and synchrony. This is kind of like the monster section where I'm hoping to share all the kind of, the kind of key simple ideas that I'm using to construct liveness strategies. So, first we're going to consider CBC Casper liveness and synchrony with no faulty validators. Or what this specifically means for us is no synchronization faulty validators. And we kind of will define this protocol that's live in this context where there's no faults in a synchronous network. So what is a synchronous network? Well, firstly, to model this, what we're going to do is we're going to assume that nodes have a clock. The validator, specifically, their state has a thing that normally hasn't been in the traditional basic CBC Casper specs, but that's a number that corresponds to the clock. And there's a special state transition called tick that updates that clock. So all validators have clocks, and all validators have transitions that tick the clock. In a synchronous network, if a message is sent, and this particular definition of a synchronous network that I'm using here, if a message is sent at time t, then it's going to be received by the other validators before they tick to t plus n. So by time t plus n, they're going to receive these messages. And here I'm assuming that no validators are faulty. And so if there's a send, there's going to be a receive by the other validators before t plus n. This is kind of the assumption. So basically, we're only considering protocol execution traces that have this property, that if there's a send at time t, it's received by all the validators by t plus n. And specifically, we're assuming here that n is a number that's known to the validators. It's allowed to define the validator terms in terms of this number n. And kind of without loss of generality for our particular solution and for ease of simplicity, we're going to assume that n is 1. So if a message is sent at time t, it'll also be received before the end of time t for other validators. So we're kind of separating time into these slots that are all one time step deep. This is just kind of for conceptual simplicity. If we let n be just some known constant, it would work out in a similar way, only we'd have to number the slots differently than we're numbering the time. And so this kind of ends up giving roughly the same solution. So I'm just going to assume that n is 1 and have this really tight synchrony bound so that we can just try to solve this liveness problem in the simplest possible case. We also need something called a plan. this plan is going to have an assignment of validator names to heights or to time slots. Basically, it says like these validators should make messages at these times, those validators should make messages at these times, and this plan has certain properties. There is some height in the plan. Do I have a laser pointer? I kind of do. Yeah, so there's a height in the plan where the set of validators is odd, which means that there is no way to split this validator setup into two evenly weighted sets. And every suffix of the plan contains all validators. So if I have these two properties, the plan is like assumed to have these two properties, and I'm going to like use these properties to show liveness of like this protocol, which I haven't 100% fully defined yet, but we're getting there. And here basically is validators are going to make a CBC Casper protocol message whenever the plan says it's their time to do so. So if it's time 20 and the validator set assigned for time 20 includes my name, then I as a validator will produce a message at time 20 before I tick to time 21. Like that's the strategy. Real simple. But even with this strategy, really simple strategy, you'd think it'd be really easy to prove liveness. But in fact, if you want to really like prove it in detail, it's still kind of a lot of work. So here is kind of how it's going to go. We're going to assume that the validator set is finite. This isn't always something we do in CBC Casperland, but it is in practice, and for liveness, it's actually necessary. Because if you assume that the validator set is finite, then we can prove this theorem, which says that every validator's clock eventually ticks. Basically, and we do this by showing that all possible state transitions, except for that particular clock tick that we're interested in, will be exhausted. So we'll get to a point where we have no possible transitions left, except for the transition that ticks the clock for this validator I. And that kind of proves and forces us to tick validator I. So let's just like suppose that we have a whole bunch of validators, and we want to prove that one of the validator I's clock will eventually tick. Then what we're going to consider is the state transitions of the overall system, and we'll try to do all of the other transitions in an attempt to never do this tick transition. And what happens is basically, all validators have to wait for validator I to make a message the next time validator I shows up in the plan for them to go beyond that point in the plan. So all the validators are kind of, at some point, going to be waiting for validator I to produce a message. And at that point, there might still be some messages that haven't been received yet, and we could propagate all those around. But eventually, all the messages that haven't been received by any of the validators so far, except for the messages that validator I has to tick forward to receive, have been received. And so we kind of exhaust all the sent messages, all of the, all the sends, all the receives, all of the clock ticks, until at some point we're basically going to get to a point where everyone is blocked on validator I, because everyone to tick past a place where validator I is in the plan needs to receive this message from validator I. And validator I maybe isn't even at that point in the plan yet, but to get there, they're going to have to tick their clock. So we can actually have this really detailed argument about, to just show that every validator's clock eventually ticks in a synchronous network where no one is faulty. And it's like, actually quite laborious to show that. Usually we take it for granted. Furthermore, every validator's clock eventually ticks, and so everyone's kind of eventually always ticking. And every validator has a next message in the plan. That's by definition of the plan, which has every validator set in every suffix. And so eventually each validator makes their next plan message. And each validator eventually receives this message because everyone's clock eventually ticks past that point. And as soon as you tick past that point, you have to receive the message. And so basically every validator eventually sends and receives the messages that are planned for. And so any prefix of the plan is eventually executed, because every message is going to be eventually sent and eventually received, and everyone's going to eventually move through this process of executing this plan. And so any prefix, any length prefix of the plan is going to be eventually executed. Now, it's possible that we have a tie at the start, like half zeros, half ones, and then like the tie continues. But there's going to be some height, by definition of our plan, that's odd, where it's impossible to have a tie. And at that point, the tie will be broken, and at all future heights, the messages will have the same estimate. And then since every validator is in every suffix of the plan, what's going to happen is if you do enough of a prefix, you'll get all the validators set repeating enough times to get a decision on this value. So and that kind of satisfies our decision criteria, finality, detector, safety oracle, construction, which kind of needs to see everyone agree and have like layers of agreement without any disagreeing messages in between. And so kind of there it is. Now, like basically by showing that I have an arbitrary section of this plan, and and eventually that gets past this tie, and then I have like an arbitrary period after that where I can have like an arbitrary number of layers. I can just, and that's kind of sufficient to show that there's a decision. So this is a rogue slide, excuse me. So that was that. That was great. So that was how we're gonna, it's like a simple strategy for achieving and improving liveness in a synchronous network with no faulty validators. Relatively simple, fixed plan with certain properties, and then making the validators send messages when it's their turn to do so in the plan. The plan has properties that like guarantee that all the validators show up over and over again, and that ties are broken so that they're showing up over and over again, agreeing later. So that was great, and even you might think too easy. Although if you really think about it, like the proof of aliveness is still kind of laborious. You kind of have to show that all the messages in the plan are sent and received by everyone, and therefore that the whole plan is executed, or at least to an arbitrary point, eventually. So liveness in general is actually quite a laborious thing to reason about and to specify, to work with, basically because you have to make this kind of argument that you run out of options except for progressing. So now I'm going to move into talking about synchronous faults in a synchronous network, or like synchronization faults in a synchronous network. And specifically, we're going to be detecting these faults because this forms the basis of it's going to form the basis of our liveness strategy in the context of faults. So let's first get a definition of what it means to have a limited number of synchrony faults in, or a limited number of synchronization faulty validators in this consensus protocol. Basically, we're going to assume that the amount of faulty validators is limited by some number number f of weight of validators, and these are the ones that are kind of we're considering some less than f of them by weight are going to be faulty. So what does this mean? Well, basically, messages sent by non-synchronization faulty validators, at time t are guaranteed to be received by time t plus n. But between synchronization faulty validators and other validators, they may not be received by time t plus n. They may not be received at all. They might be received later. So between non-synchronization faulty validators, we have the normal synchronization conditions. But between a synchronization faulty validator and another one, we may not have this message arrive before t plus n. So if you look at a complete protocol execution trace, you can actually see which pairs of validators are synchronization faulty. You can see who sent a message that didn't arrive within n of the time it was sent. And so you can the complete execution traces and look at pairs of validators and see, actually, by inspecting the trace, whether or not there was a synchronization fault between those pairs. So basically, we can draw a graph between validators with nodes as validator names, and edges between them for validators who haven't experienced through the execution trace any synchronization faults. So this kind of graph I call a connectivity graph. It draws the reliable connections between the validators. And so kind of if we have a limited number of crash faults or these synchronization faults, then what's going to happen is like there's going to be some less than f total weight number of nodes that we can remove from this graph to reveal a totally connected graph, like a fully connected graph. And this fully connected graph we could imagine, be the graph of non-synchronization faulty validators who to each other won't ever have synchronization faults. And so basically, if you look at a complete protocol execution trace and construct the connectivity graph, and the connectivity graph has the property that you can remove less than f weight of nodes from them and be left with a fully connected graph, then that trace is a protocol execution trace with limited synchronization faults, specifically less than f weight of faulty validators. So by looking at the connectivity graph from an execution trace, we can tell whether or not a particular execution trace satisfies this definition of having less than f faulty weight of validators. And this may not necessarily be efficient to do, and we don't actually need to do this, but we need to but this is the way that I'm expressing and understanding the assumption that there are limited number of faulty weight validators. Basically what that means is that at least for total weight minus f of the validators, there is a fully connected clique, meaning that the validators in that clique haven't ever had a synchronization failure between them. And in a synchronous network, that's a reasonable kind of assertion. So basically, I'm going to define the synchronous network as basically having execution traces where this connectivity graph has this property that if I remove less than f of nodes, I'm left with a fully connected one. Like that's the definition of a synchronous network with limited faults in my context. There's like really good reasons why I do this instead of having, say, for example, a validator that I consider to have Byzantine behavior. But we can talk about typed fault tolerance analysis versus Byzantine fault tolerance analysis a little later. So now we're going to give a protocol that in some way learns this connectivity graph. Basically, it's a really simple protocol. Basically, every validator, when they produce a message, commits to the next time they'll produce a message. It's called the next message time, sometimes just NMT for short. And it has to be later than the current time that they're sending a message from. So NMT is like a next message time. It's a commitment for when you'll send a message in the future. And this is going to be used by validators to tell whether or not there's been a synchronization fault. Like if you tell me you're going to make a message at slot 10, and I don't hear from you by the end of slot 10, then then we've had some kind of synchronization fault between us. And so each validator can maintain in their protocol state a fault attribution map, where basically they consider their peers as faulty or not, based on whether or not they've had a synchronization failure with them. And if you don't receive a message from a validator by the end of their next message time, then you mark them as faulty. And the next message time is unconstrained, except for that it has to be in the future. And just from this kind of construction, we're going to get some pretty kind of powerful stuff. So notably, if you take if you take a protocol state of a validator, you can tell who they've marked faulty. And if you look at the latest message, their latest message, you can also tell who they marked faulty. And so if you look at the latest messages from a bunch of validators, you get to kind of build the connectivity graph for the network by seeing which pairs of validators haven't marked each other as faulty. And there's this key theorem, basically, where in a synchronous network with limited faults, these fault attributions eventually stop changing. So in all protocol executions, there is an index, after which point the fault attributions stop changing, where basically, all the faults that have been expressed, all the faults that will be expressed have been expressed. Could be because all the possible faults have been expressed, but it could be because just the attacker is going to stop at that point, only having shown certain faults. But no matter what, in all protocol execution traces, eventually the fault attributions stop changing. And this is kind of like a cornerstone kind of thing. Basically because what this means is that or let me just restate this kind of for the connectivity graph. Just like the fault attributions stop changing, the connectivity graph also stops changing because a faulty node can at any point say disconnect from a node they're connected to, but they can never reconnect. And so they're kind of spending and never getting back their budget of faults to display. And so at the end of the day, eventually the connectivity graph and fault attributions become stable. So for this really simple next message time protocol with fault attribution, very, very simple protocol, we have this property it's not liveness, but it says that eventually, if you go far enough in any of these execution traces, we're going to have the connectivity graph and the fault attributions stop changing. So that's like an intermediate protocol, which we're going to use in order to come up with a protocol that's live in Synchrony for CBC Casper. But since we're doing pretty good on time, I guess I'll stop for any questions if anything's not clear. So far I've covered two very simple protocols. One of them, you have like validators assigned to particular time slots, and that's when they make their messages, and they all make it according to plan, and then we have liveness because the plan at some point has a tiebreaker. And then you have this other protocol, which is this next message time protocol, where validators commit to when they're going to make new messages and mark each other as faulty when they don't receive messages from each other in time, and where we have this property that eventually the fault attribution and the connectivity graph stop changing. Hopefully that's pretty clear. Really, really simple protocols. And here's kind of the link, or like the kind of combining the pieces together to come up with a fault-tolerant liveness strategy. Basically, it turns out that like a stable fault attribution or a stable connectivity graph is kind of similar in some ways to a network without faults, because along those edges where they're connected, the synchronization faults don't occur eventually, because eventually this thing is stable, which means that eventually synchronization faults stop occurring, which means that it's very similar to just a regular network with no faults. But here, we can't really have a fixed plan, because if we had a fixed plan, then we might end up with like some unexecutable plan, because like some validators that we're relying on being in our plan ended up being faulty and hiding away. So instead, we have something called a planner. What a planner does is it takes connectivity graph, specifically the largest connected component of that connectivity graph, and returns a plan for the validators in that connected component. And it's similar to the plans that we discussed earlier, only instead of having an odd set somewhere, we have to have an odd set in every suffix, because now we don't really know at what point this plan will start being executed. We know that eventually, eventually we're going to have magic happen, but like it could be that at the start, things don't get executed according to plan, and so we need to have an odd set of validators later on. And here's another additional requirement for the plan that kind of existed before, but only implicitly, that validators with adjacent positions in the plan are connected, meaning that they haven't experienced each other have synchronization faults, and once we get to the stable condition, they won't in the future experience each other as having synchronization faults. So 3 properties of the plan at this stage. Every suffix contains every validator in the largest component of the connectivity graph. Every suffix contains an odd set of validators, and the validators in adjacent positions in the plan are connected in the connectivity graph. So these three things together, with the following constraint, namely that sorry, wait a second. So basically, if your validator name appears in the future of the plan, then your next message time has to be the time at which your name appears in the plan. So basically, like the next message time in the next message time protocol was completely unconstrained. Now here I'm insisting that if your name is in the plan going forward, that you choose your next message time to be exactly the time at which you're included in the plan. And what this basically does is it will it serves as like a refinement of our next message time strategy that specifically says where people should put their message, when people should make messages, and specifically according to this plan. So basically, the next message time fault attribution system guarantees that we're going to have an eventually stable connectivity graph. And from that point on, all non-synchronization faulty validators will have the same connectivity graph because they're connected to each other, and so they're learning the connectivity graph like through the connections. And so each one of these validators are learning the same connected component. And so all the correct validators end up having the same plan because the planner takes just that connected component as input. And so all the non-synchronization faulty validators learn the same connectivity graph or the same connected component of it. And then they give that to the planner, and they all come up with the same plan. And after they make their next message, they're going to be synced up with this plan in the sense that like their next message time is going to be exactly in the same plan that they all have. And basically, adjacent validators in the plan are connected in the connectivity graph. And so they're able to build messages on top of each other because basically otherwise there would be a synchronization fault, which would be a contradiction of our assumption that we have this eventually stable, or that we've reached the stability point of the connectivity graph. And so, if you assume that you've got to the stable connectivity graph point, then what we're going to guarantee in like pretty soon, basically so you get to the stable connectivity graph point. Pretty soon after that, all the correct validators or non-synchronization faulty validators have the same connectivity graph local component, which gives them the same plan. And after their next message, they're all synchronized with that plan. And so after that point, that plan is going to be executed exactly correctly for an arbitrary suffix after that point. And so, or like a, arbitrary prefix of the suffix after that point. And so, very, very similar argument to the previous plan about why this is live, right? We have enough validators in this connected component because it contains at least all the non-synchronous faulty ones. And eventually there's an odd height. And eventually after that we get any number of layers of the validators seeing each other agree with the results of that tie breaking. And there it is. That's basically the story about how we can basically combine these two ideas of a plan and this eventually stable connectivity graph in order to come up with something so that all of the non-faulty validators can coordinate around exactly what they're planning to do and produce like this blockchain or this shape of messages, which is guaranteed to eventually have a decision. And kind of all of this is basically thanks to synchronicity, which guarantees that correct validators are able to synchronize, and therefore that they're able to execute these plans, like they're able to produce messages after each other. So I hope that makes sense. But again, let's recap. Next message time protocol leads to eventually stable connectivity graph. The planner takes the largest connected component of the connectivity graph and returns a plan. All of the non-synchronous faulty validators are going to be connected to the same component, so they'll have the same plan. And the connectivity graph eventually is not going to change, which means they'll be able to synchronize properly with their adjacent nodes in the synchronization graph, in the connectivity graph, which are exactly the nodes that they might be neighbors to in the plan. So the plan is going to execute correctly, because the plan is basically along the edges of the connectivity graph. And so we get an arbitrary amount of the plan executing. But here, rather than having the plan be like defined from the start, the plan is defined as a function of the connectivity graph. And that ends up being fine because all of the correct validators, or like the non-synchronous faulty ones, observe the same connected component. And that's basically because they're connected to each other. And so they get to kind of learn that just by sharing with each other this information about their local area. So I hope that's pretty clear. Hands up if this makes sense. Do you understand the protocol? It's pretty good. All right. And if you don't understand, do you have a question? More questions, anyone? We can do more questions later. But this is all going way faster than I expected. I have so many slides, but they don't take much time. All right, well, I'm going to assume that you're shy. Oh, there we go, the lights. Nice, you guys are on the spotlight now. But still no questions, okay. Well, we can move on for now. And if you have a question, I'm not sure if I just didn't see your question. Okay. You can also hit me up later. So liveness and partial synchrony. What is this going to be like? Well, it's kind of similar, but partial synchrony isn't exactly like synchrony. Let's kind of define it. It's kind of similar. A message that's sent at time t will be received by the end of time t plus n. But in this case, instead of this n being known to the validators, n is it's not known. There's no known bound on n that any of these protocol nodes could ever use. N is basically like not something that they get to touch. The validators don't get to know n. Partial synchrony in some way is like synchrony with an unknown bound on the message delays. So because it's unknown, you never really get to know when you receive a message too late if it's above the bound or not. So we have a solution here with a couple of parameters. We have an increasing sequence. Here I call f. It's not the best name. This is a sequence of waiting times. So this validators are going to have the strategy of waiting longer and longer in order to do this trick that I'm going to explain in a second. So if a validator, and we keep this number, which is the number of times that we've received messages later than expected. And basically, f of nij is going to be like the amount of time that validator I waits for validator j after their next message time. So this increasing function is basically the increasing delay times that you're waiting to receive messages. And the plan is very similar to before. And basically, every suffix has every validator and an odd set of validators. Previously, because we were able to perfectly execute everything in a synchronous network, we only needed one odd position. But because now we might have some kinds of faults at first, we need to always have an odd one later. And furthermore, I kind of have this constraint where every validator kind of appears once for every time every other validator appears once. So like between every two instances of the same validator, all of the other validators fall in between there or parallel, like in between or in parallel. And so basically, between every validator, there's no validator appearing twice. This is kind of a constraint that I have so that I can calculate my next message times. We'll talk about that in a second maybe, but the plan here is a little more restricted than before. Before I was like totally cool with like a validator producing 50 messages, 100 messages before any other validator produces any. Now I'm kind of constricting it and saying like, look, every validator should only make one while all the other validators are making one. And there was like another option that I had other than doing this, which is like to give the validators the ability to submit multiple next message times. But it's a little bit technical, so let's kind of skip that conversation for now. So basically, the next message time is going to be chosen as the maximum of the next message times of the validators in the preceding step of the plan, plus the amount of delay that you're waiting for them. So imagine if I'm validator 12 and I'm waiting for validator 9, 10, and 11 who are making messages in the previous slot, and they have next message time 9, next message time 10, and next message time 11, and I'm waiting for them, F, N, like 12, 10, 12, 9, 12, 11. So like the next message times plus the waiting times is like how much I'm going to wait for individual one of them. And the one that is latest is basically how long I'm going to wait for all of them. And so my next message time is going to be set up so that if everything goes well, if I get messages before these timeouts, that I'll be able to produce my messages in the plan having received messages from everyone previously in the plan. So the next message times are calculated using the next message times of the validators in the previous slot of the plan. And this is kind of why I wanted to have all of validators only have one message each for each message each, because if you had like 50 messages there and I only know your one next message time, I might not actually know the next message time that you have like right before my slot. And so to calculate this next message time, I'm using this restriction that I know the next message time of each of the validators right before my next slot. And I know that because there's no way basically because there's no way for them to appear in the plan if, sorry, I know that because I have their next message time, basically. I got a little confused there because I started thinking about the faulty context. But right now, we don't have any faults. Basically what happens is you're going to increment this number every time you fail to receive a message by the expected time. And so what that will do is it'll increase the amount of time you're waiting for messages from that validator. From F Nij to F Nij plus 1. And so this incrementing of this number increases the amount of time we're waiting for messages. And so basically we can start to show liveness by basically showing that eventually validators stop receiving messages beyond their waiting times. So we basically stop having the synchronization failures that occur because of partial synchrony. There's basically two ways for these things to end. One of them is this F at Nij ends up being bigger than N, which means that the amount of time that we're waiting is enough. Like there's this unknown bound on how long messages are going to take, and we're waiting more than that eventually. Because if it fails enough, this increasing waiting time is eventually going to get over that fixed unknown constant N. And at that point, we're going to be waiting long enough to receive these messages. Or the other alternative is maybe we never get over that N, but still, nonetheless, messages always arrive before our waiting time. Also possible. Also possible to have that. And so, but there's no intermediate kind of thing where we keep always getting more delays and more synchronization failures. So eventually what happens is there stop being synchronization failures. Eventually, validators that are waiting for messages from these other validators will receive them before they make their next message. And what that will lead is to the correct execution of this plan for an arbitrary period of time, and kind of very similar to before, this is going to lead to liveness, because eventually you hit this odd thing that breaks the tie, and eventually you get any number of layers of agreement afterwards. So, partial synchrony with no faults is quite different than partial synchrony than synchrony with no faults, because in synchrony with no faults, we're able to perfectly reliably execute a plan. In partial synchrony with no faults, we can't really do that. We're still going to have faults in some extent, even though we don't have faulty validators per se. Like we don't have synchronization faulty validators. We just have faults that occur because messages take longer than expected, because we have no known bound on how long they might take. So in partial synchrony, it was impossible for us at the get-go to prevent these synchronization failures, even when all nodes are considered to be honest. But eventually, we will have exactly the same scenario, because eventually our timeouts get long enough, or we just stop receiving messages beyond them, so that we don't have any more synchronization faults. And so basically, partial synchrony eventually kind of feels like synchrony, because eventually we wait long enough. I mean, because the main difference between partial synchrony and synchrony is whether this bound on message arrival time is known. Great. So I hope that makes sense. And, you know, I know you guys don't like questions, so I'm going to keep moving. So now, basically, we're going to be doing something analogous to the fault detection thing that we were doing before, only now we're doing it in a partially synchronous network. We can't really be certain when we receive a message later than this timeout, whether they were faulty, whether the sender was faulty, or whether just the partial synchrony bound is higher than our current estimate waiting time. There's no way to know. And this is kind of the tricky thing about partial synchrony. It's like we don't really know what happened. Like, was the guy faulty, or was the network is this just what the network is like? However, if we do assume that our bound is high enough, then we know for sure that it was a faulty validator. Like, if we know that our bound is high enough, then the only way that we could have missed this synchronization is with the faulty validator. And so basically, if you don't receive a message in time from someone, you're going to increase your F and N. So you're going to increase the amount of time you wait. And so eventually, you're either going to stop receiving messages from them that are late, or you're going to increase above this bound. But in either of those cases, you basically are no longer having synchronization failure with that node if they're correct, or if they're not faulty. So basically, what we basically have is the following. Eventually, non-synchronization faulty validators stop receiving each other's messages later than expected. So, well, that's one thing, right? So non-synchronization faulty validators eventually will just start always receiving each other's messages. And so eventually you're going to get to a point where the only messages you're not receiving faithfully from are from non-faulty validators, because eventually sorry, I meant from faulty validators. So eventually, from all the correct validators, everyone's receiving and sending messages in time. And only the non-correct validators are showing faults. And then, because eventually this bound gets high enough, or these messages stop being delivered late. And so basically, what we're going to do is something like this. We're going to have, previously we kind of had this little state where basically we were connected to a validator, and then we marked them as faulty whenever we had a synchronization failure. Now, this was kind of in our synchronous fault detection scheme. Now, because we don't really know when we mark them as faulty whether that was a correct thing to do, we have to have this forgiveness direction, where basically we will unmark them as faulty after some time. And so here's kind of the strategy. Basically, we're going to be connected with the validator, and we're going to wait some amount. And then if the message comes in too late, we mark them as faulty. And eventually we forgive them, and we wait longer. Every time we disconnect from them, we wait longer and longer. And then eventually, for correct validators will permanently stop moving from connected to faulty. Because correct validators, eventually, this time is going to be high enough, or they'll just stop sending delayed messages. And so eventually, for all correct validators, you'll always stay in the left state there. Yeah, is there a question? I thought I saw something. Sorry, I can't hear you. Can you speak up a little bit? Comfortable slashing? Sorry, 1 second.
Possibly a dumb question, but after the forgiveness period is over, is there some sort of like punishment or slashing or something along those lines?
So at this point, this is just like a consensus protocol specification. Like there's no market design, incentive design stuff here. But the fault detection model in some way was like conceived of in the context of proof of stake, and I think it lends itself to this kind of thing. So definitely like I don't see it likely that being marked faulty is going to be consequence-free. However, kind of not really the scope of this talk. This is just about distributed systems, consensus protocols, not really proof of stake. So the idea here is, correct validators eventually start like staying in the connected one only, because you stop having accidental disconnections from them. And then faulty validators can go back and forth between faulty and connected by just showing a fault and then waiting to be forgiven. But because of the increasing forgiveness times, faulty validators spend more and more time there. And so there's more and more time where this thing is kind of stable. So non-synchronization faulty validators eventually stop marking each other as faulty, and they eventually forgive each other. And so here's kind of like our key theorem for this one. Eventually, we have a stable connectivity graph for long enough. So imagine we have a similar construct for connectivity graph, where basically we draw an edge between nodes if they're marking each other as correct. And you could imagine that because of this pattern that I described earlier, where eventually correct nodes stop marking each other as faulty, and faulty nodes get marked as faulty for longer and longer, as it takes longer and longer to forgive them, eventually we'll have a connectivity graph that's stable for an arbitrarily long period of time. So in a synchronous network, we had like a permanently stable connectivity graph. Now in a partially synchronous network, we have a slightly weaker result, but it's stable for some time. Yeah. So this eventually stable for arbitrarily long connectivity graph is going to provide our basis for liveness and partial synchrony in the context of faulty nodes, along very similar lines to our previous strategy in the synchronous network. Only instead of having like a permanently stable connectivity graph, we're going to have like a stable for long enough graph. So similarly to before, we're going to have like a planner instead of a plan, because our plan is going to have to change as a function of the connectivity graph, which before was kind of all fully connected because we kind of knew that everyone was correct. And now, the connectivity graph is going to change, and the planner is going to return again as a function of the largest connected component of the connectivity graph. So we have similar properties for the validator, but instead of having every suffix have an odd one, now we kind of need any long enough period inside to have one, so that like if we have like a long enough period at some point, we'll be able to make a decision. So the planner has like slightly different criteria. Next message time is calculated exactly in the same way as in the partially synchronous thing. You like look at the people in the previous slot in the plan, ask what their next message times are, plus the amount of time you're waiting for them. The maximum of those is the next message time. And similarly, basically, between non-synchronization faulty validators, there stops being failure. There's only failure between synchronization and non-synchronization faulty validators. And so this thing is going to be basically stable, and the validators that are connected while it's stable are able to send messages back and forth. And because this is stable for an arbitrarily long period of time, we get to execute an arbitrarily long section of the plan, which leads to this odd thing hitting and then whatever number of layers of agreement that we need for a decision. And so very, very analogous to our original kind of setup, we have liveness and partial synchrony. Great. So now I'm going to go to just quickly look over some future work that we need to do. So this stuff, the synchronous stuff has been formally specified. Formal verification is still kind of ongoing. Formal specification of the partially synchronous one hasn't been specified. We just have informal verification of both of these at the moment. We need to come up with practical planners that can basically like sketch nice things through connectivity graphs efficiently, that hit all the validators and which have these properties. We need to have basically reasonable increasing waiting times and forgiveness times. And this is all for the binary consensus. This all kind of can naturally be extended to blockchain and other kind of consensus protocols. And it kind of needs to be. We also are interested in kind of weaker notions of partial synchrony, where we have like clock drift, and there's multiple notions of partial synchrony, and kind of we are curious and like to come up with solutions for different ones. And the weaker the assumptions, the more kind of broad of a context we have liveness in. And in this context, we kind of have a solution. On sketch paper, like not clear if it's 100% correct, but basically it's just like the bound calculation is tricky because like you have to translate clocks from like the remote clocks to local clocks in order to figure out your next message time. But it's kind of very similar story. We also want to worry about performance, like making sure that the overhead and latency aren't affected by faults. Like all of this showed is that like the faults can't stop a decision forever. It doesn't say anything about how long it'll take to make a decision. And it'd be good to have some notion that we have robust performance. So basically, we were able to come up with liveness strategies in synchronous and partially synchronous networks. And somehow, similarly to how we did it for consistency using equivocation fault detection, this time we used synchronization fault detection. Either perfectly reliable or eventually reliable fault detectors. And with these fault detectors, we can build this connectivity graph, which show us where there aren't faults, and therefore where we can successfully send messages back and forth. And we can use that to plan how the messages are going to be sent in order to have kind of liveness through the execution of a pattern of blocks or messages that leads to agreement. So, a network with a stable connectivity graph is a lot like one without faults. That's kind of like the key kind of, those were some of the key kind of ideas that went into this research. Well, thanks a lot for listening, and please come for my crypto law talk tomorrow. Really appreciate it. And if you have any questions, it says here I have a minute and a half. I don't know. Jacques.
Actually, you talked about it in the conclusion when you say clock drift, but how do you handle cases where you receive messages from the future because of clock drifts? Like, how could you have...
So the idea with clock drift is like, you translate other people's clocks into your clock. And so, imagine if the clocks are all kind of big O linear in each other. Then you can kind of have like a linear transformation between like their clock and your clock. So you interpret their time in your time. And if you sample basically messages from them over time, like they say they sent a message at time 10, 20, 30, and 40, and you received it at 15, 30, 45, and 60, you kind of have some notion that your clock is running 50% faster. So we're using the differences between their message times on their local clock and when you receive them. You can kind of do translation of the rates of the clocks, and that ends up being a lot of the puzzle for doing that kind of coordination.
Okay, but what about the other way around? Like really when you receive a message that, like in a time that hasn't happened yet for you, even if you translate it, you don't know exactly.
Yeah, so I mean, in some extent, these are going to be estimates, and if the estimate of when this was sent is in the future, I mean, I don't know if that's. I don't know how relevant that is exactly, but basically what's going to happen is like you're going to if the message comes too late, then you mark them as faulty and wait longer. Here it's coming too early. So I don't know. I mean, that's a good question. No answer on top of my head. Sorry.
It's okay. I have a hard one for you.
Sure.
Well, sorry. What about Byzantine failures? Like, what if you start getting?
Yeah.
Have you thought
Yeah.
about?
So we have this like
that?
amazing theorem that I would love to share. Basically, that like kind of relates and shows how we can relate Byzantine fault tolerance analysis to this typed fault tolerance analysis that I'm doing here. And basically, like for validating protocols that can like only receive messages that are like valid in some sense. They can only take traces that are valid in some sense. And so we can look at the Byzantine cases just in terms of the valid traces. And the faults that are observed there are basically of particular types, like, for example, synchronization faults and equivocation faults. And I can kind of show that, like, okay, if I can look at all of the traces, that like whatever Byzantine faulty traces are definitely in there, because if I'm looking at everything, whatever undefined behavior you give me will also land me somewhere in that everything. And so I have like a foundational theorem that tells me like why I don't need to worry about untyped fault tolerance analysis and why looking at the typed faults is kind of enough. Yeah, it's cool. Come find me after.
Okay, I will. Thanks.
Thanks, guys.